Okay, yeah. So just go ahead and try that, and then we'll work it together in just a minute. Okay, so when we do this problem, to figure out that it's partial fractions, there are two conditions that we kind of talked about last week that we're going to talk more about today. One is that the degree of the top has to be smaller than the degree of the bottom. So like here, the degree of the top is 1 because the largest power of x is x to the first, and the degree of the bottom is 2. So the degree of the top has to be smaller. And then the second is that the bottom has to factor. And so 9x squared minus 16 does factor as a difference of two squares. So to do partial fractions, we're going to rewrite this as 3x plus 12 over, and then the bottom factors as 3x plus 4, 3x minus 4. And now what we kind of said last week is that you break that into smaller or component fractions with smaller denominators, where we do like a over 3x plus 4 plus b over 3x minus 4. And the goal at this stage is to solve for a and b. Does that make sense to everybody? Any questions? Feel free to unmute yourself if we're not sure on something, or type it in the chat. That's fine too. Okay, so then we're going to clear the fractions. So to do that, you multiply by the common denominator. So you multiply by 3x plus 4 times 3x minus 4 over 1. And that distributes on the right-hand side and it multiplies on the left-hand side. So on the left-hand side, both factors in the denominator cancel. So you get 3x plus 12. On the right-hand side, this 3x plus 4, 3x minus 4 distributes. Yeah, I just saw this question in the chat. Can it be the other way around? Yes. So if you have a over 3x minus 4 and b over 3x plus 4, that's fine. But your a will be my b value, and my b value will be your a value, vice versa. So, but the important thing is, like, if a ends up being 7, then whichever one you have with 3x plus 4 should be 7. I don't think it is 7, but whatever it ends up being, that's the case. So, okay, so on the right-hand side, on the first fraction, the 3x plus 4 cancels. So you get a times 3x minus 4. And then on the second fraction, the 3x minus 4 cancels, so you get b times 3x plus 4. And now you distribute the a and distribute the b. And now we're going to combine like terms where the variable's x. So we're going to combine like terms on the right-hand side, grouping all the x's together. So we get 3a plus 3b x, and then plus negative 4a plus 4b as the constant term. All right, any questions to there? Everybody good? All right. So then now you're going to try to, we're going to set the coefficients equal to each other. So the polynomial on the left has to equal the polynomial on the right. So on the left, we've got 3x plus 12. That means this has to be 3x plus 12. So that means 3a plus 3b has to equal 3. And then negative 4a plus 4b has to equal 12. And so there are several ways to go about this. Last week, we were trying to get these to match up. I'm going to do the same here, but one thing I would notice on this is that I could divide the top equation by 3 and get it so that a plus b is equal to 1. And then I could actually divide the bottom equation by 4 and get it to be negative a plus b equals 3. And now if I add those, the a's cancel out. And I get 2b equals 4. So b is 2. And now I can go back and get a plus b is 1. Or, well, all right, yeah, that works. And then a plus 2 is 1. So then a is negative 1 in that case. Does that make sense to everybody? So now we rewrite this as a over 3x plus 4. So that's negative 1 over 3x plus 4 plus b over 3x minus 4. So plus 2 over 3x minus 4. And now we're going to do this as two separate integrals. So we're going to split that up and do two separate ones. That's more straightforward. Does everybody follow to there? Any questions so far? All right. So now we're going to split this into negative 1 integral 1 over 3x plus 4 dx plus 2 integral 1 over 3x minus 4 dx. And now these are both quick u substitutions where u is the bottom and du in both cases is 3 dx. So we get a 3 inside and a 1/3 outside on both of those. And so that's where we get 1/3, negative 1/3 for the first one, and then we get positive 2/3 for the second one because of the positive 2. And so that should be your answer. So what we're getting, you guys, everybody following that? Okay. Any questions at all so far? You guys all good? Okay. So the way that partial fractions can get more difficult or more involved is a few different things. So there are two conditions that we talked about this having to meet. So for partial fractions to work, one is it must be a proper rational expression. Meaning that it's a polynomial over a polynomial. Polynomials are things like 3x plus 12 or 9x squared minus 16, where you have a biggest power of x. The biggest power of x is a positive integer or maybe 0, like it could be technically 4. which would mean it'd be 4x to the 0. But normally you have x to a power. And then all powers below that are positive integers, so or 0. So you have x squared, x to the first, x to the 0, but no negative exponents, no square roots of x, no fractional exponents, nothing like that. No trig, nothing like that. So you have a polynomial over polynomial. And then, so that's what a rational expression is. Proper means the degree of the top. Whoops, dg of the top is strictly less than the degree of the bottom. So degree on the top, the degree is the largest power of a polynomial when you have it in terms of one variable x. So the degree of the top here is 1, the degree of the bottom is 2, 1 is less than 2. That means this is a proper rational expression. If the degree of the top is bigger, or if the degree of the top and the bottom are equal, you have to do something else first. So this works when it's a proper rational expression. And then the second condition is the denominator must be reducible. Meaning basically it has to factor. The thing about that is that factoring in calculus may mean something slightly different from what it would have in algebra. So in algebra, you for sure would have said, okay, x squared minus 25 factors to x plus 5x minus 5. You for sure would have said that x squared plus 25 is prime, meaning it does not factor. Does everybody get why? Okay, but then if you have x squared, say, minus 7, in algebra, you probably would have said that's prime. In calculus, we're going to factor that into x plus the square root of 7, x minus the square root of 7. And so if you had a problem like this with x squared minus 7 in the denominator, you would do it much like the problem we just did. The square root of 7 would make this kind of nastier down here, but we would do the same basic process. The integrals at that stage would be about the same. You'd have a number over x plus the square root of 7, a number over x minus the square root of 7. Just like this, you'd use log, and the calculus part wouldn't be that hard. This algebra would be a little bit worse, but we do factor things like that down. X squared plus 25 doesn't factor unless you allow for I, and in standard calculus, we don't allow for I. So we do not allow for the square root of a negative to exist. If you do allow for I, meaning you consider all complex numbers, then this would factor to x plus 5i, x minus 5i, and we won't do that in standard calculus. You can take a course called complex analysis where you would look at what happens when you allow for that, but we don't allow that here. So x squared plus 25 is prime, and it's more exactly what we consider an irreducible quadratic. So this is called an irreducible quadratic, which means even over the complex numbers, you cannot break that down at all. Does that make sense to everybody? Everybody clear? Okay, so it has to be proper. The degree of the top has to be smaller than the degree of the bottom, and the denominator must be reducible, which means we have to be able to factor it somehow. We might not be able to factor it using standard methods from algebra, but there is a way to factor it, meaning there is a root, and so there's a way to do it. When those two conditions are met, then we can apply partial fractions to break it down into smaller things. Now, there are two parts of partial fractions that we need to be concerned with. One is, so the kind of the new part is, okay, how do we do this? So what does the breakdown look like? So what does the decomposition format look like? Okay, so what does the decomposition format look like? And then once we do that, how do we then do these integrals? How do we evaluate these? And so there are other cases where we don't get factors that look like 3x plus 4 or 3x minus 4. When they're not these types of factors, the numerators might actually be different from that. And the way we evaluate the denominators might be, or the way we evaluate the integrals might be different from this. And so all the examples we've looked at so far have these types of factors, which we'll call linear factors, because it's x to the first power. So these are linear factors. They're what's called distinct linear factors, which means the factor here is completely different from the factor here. 3x plus 4, 3x minus 4 are completely independent factors, even though they're both 3 and 4. This is negative 4, so it's actually a different factor. So when that happens, so what can happen is we could have what's called repeated linear factors. We could have what's called irreducible quadratic factors, meaning you might get x squared plus 25 as one of these. And the way we handle those things are different from problem to problem. So I want to look at a few examples, and then I want to kind of talk about the general case. But we need to know what happens when these things aren't true, and then, okay, even when they are, how do we determine this format of the decomposition in general so they're not all like what we've been doing so far? And then once we get to here, how do we handle those integrals? Any questions on that so far? Okay, so we're going to go on to another example. And I want to show what happens when we have a repeated linear factor. And let me get this one real fast. My bad. I had it pulled up and I don't now. So my fault. All right, so we're going to get the integral. What's it tell me? X plus 2 over x squared plus 10x plus 25 dx. Okay, so we're going to look and see what happens when something slightly different happens on the bottom. This looks just like the other problems we've been doing. So one thing, it is a rational expression. We've got a polynomial over a polynomial. It's proper, meaning the degree of the top is smaller than the degree of the bottom. So degree 1, degree 2, and the bottom factors. So let's go ahead and do that and start partial fractions. But we're going to see something slightly different happen when we factor. So when we factor x squared plus 10x plus 25, you get x plus 5, x plus 5. And so when you get something like that, both of those factors are considered linear. They're x to the first power. But these are the same factor twice. And so when that happens, what we do is we rewrite it as x plus 2 over x plus 5 squared. And what this is called is a repeated linear factor. Okay, so it is linear, but it's there twice. And so the way we handle that in the decomposition is slightly different. And then the way we handle the integral is slightly different because of what we end up with when that happens. When you have x plus 5 squared in the bottom, I want to think back to algebra for a second on a different type of problem. So the idea is you're trying to come up with a bunch of fractions that add up to whatever the common denominator that you have is. Okay, and so let's say the common denominator was, say, x to the third power. What denominators could result in something having a denominator of x to the third? So one thing is x to the third, but what other smaller things could result in x to the third being the common denominator? You guys remember?
What Wouldn't else? It be just x?
Yeah, just x, and then one other thing as well. So x does, but what else? So x squared, even though 2 doesn't go into 3, x squared does go into x to the third. So x squared, and x to the third, if I look at those three denominators, the common denominator of all three of those would be x to the third power. Does that make sense to everybody? Do you follow that? Okay, so with that in mind, that's how we handle this. We're looking for all of the things that could contribute to this being the common denominator. And so when we have x plus 5 and x plus 5 squared, we split it, or when we have x plus 5 squared, we split it into a over x plus 5 plus b over x plus 5 squared. Okay. Does that make sense, everybody? Okay, now we're going to solve this for a and b just like we did before. What we're doing is the same, but the algebra looks a little different. So when we multiply through by the common denominator is x plus 5 squared, and we think of it as being over 1. And so now when we multiply through, the left-hand side, both factors of x plus 5 cancel. On the right-hand side, on the first one, you've got 2 x plus 5s on the top and 1 x plus 5 on the bottom. So one of them cancels, and you get a times x plus 5. On the second one, both x plus 5s cancels, so you get just b. Does everybody follow how that worked? And so one thing we said last week is that when you're doing the intro problem, so all the ones we were doing so far, and then even this one, it looks like you're cross multiplying, and you kind of are when there's only 2. So, but the reason that is because one of them cancels and the other one's what's left over. In general, you're not cross multiplying, and that's not technically what we're doing up there either. You're canceling with this common denominator. So it's like, okay, both of these cancel, or one of these 2 cancels with one of these, leaving 1 left. And then here they both cancel, leaving none of them left, and the only thing that's left is b. Over here, same deal. They both cancel, so the only thing left is x plus 2. Now we're going to solve it the same way we did before. So we're going to distribute the a. And we're going to combine like terms, although it's kind of already in the order we want. But we're going to still group it so it's clear. We've got something times x plus some constant, and the constant is 5a plus b. Everybody follow to there? Okay, so now from here, a has to be 1. So we get a equals 1, and then 5a plus b has to equal 2. Well, the way you solve this one is a little bit more straightforward because we already know what a is. So you plug a into the second equation, and you get 5 times 1 plus b equals 2. So then b is negative 3. Does that make sense? Okay, so we get this to split up into 1 over x plus 5 plus negative 3 over x plus 5 squared. And now all the stuff at the bottom of the screen is the work for how we broke it into these 2 fractions. And we get the integral of that times dx. Everybody good? Okay, so now we're going to split this into 2 separate integrals. For the first one, it is a log form. But for the second one, we're going to pull the negative 3 out. And it's not a log form. We're going to want to rewrite that as x plus 5 to the negative 2 power. Everybody clear why? We're going to do a u substitution technically, but it's going to be u to the negative 2 du, and so we're going to use the power rule. So now on both of these, u is x plus 5, but in those cases, du is just 1 dx, so we don't really need to go through the u substitution. This one is natural log absolute value of x plus 5. This one, though, is 1 over negative 1 u to the negative 1, so x plus 5 to the negative 1 plus c, and now we're going to simplify that and get log absolute value of x plus 5 plus 3 over x plus 5 plus c, and now that's the answer. All right, any questions on that? Pretty good. Okay. So now, like we said a few minutes ago, there are a few different things that can happen. And so it's like, how do we evaluate, and then what's the decomposition format? So down here, the format of the decomposition is a little different from what it was before. And then the way we evaluate the integrals, the first one was the same because it was log, but the second one was different. It was power rule. Does that make sense? And so I want to talk about the different cases as far as what can happen. So you can have several different types of things come up when we're dealing with partial fractions decomposition. So when we factor the bottom, okay, so two things, degree of top, and let's make that legible, degree of the numerator needs to be less than the degree of the bottom. And then you need to factor the bottom. Okay, once we do that, there are 4 different cases for what we can do or what we can have in the bottom. So in the denominator, you can have distinct linear factors. You can have repeated linear factors. You can have distinct irreducible quadratics. And you can have repeated irreducible quadratics. So these are what we will see as far as breaking these down. We won't actually do integrals of all of them, but we'll do everything except repeated irreducible quadratic. We'll kind of talk about how that works, but not do actual integrals involving them. So, okay, so there are 3 things to consider with each of these. So one is, what does it look like in the problem? Okay, so these are repeated linear. So, or I'm sorry, these are distinct linear. This one is a repeated linear, and then we want to know what the other ones look like. So we want to know what it looks like. We want to know how to handle the decomposition. So once it does, how do we do this A and B stuff? So how do we do the decomposition? And then once we get to the integral, how do we handle the evaluation of those integrals? And so we're going to kind of summarize that here. So what does it look like? So that's when you have whatever over like 2x minus 5, or whatever over x plus 6, or whatever over x. Does that make sense to everybody? So it's mx plus b. It's x to the first is the power. So you have mx plus b, mx plus b, m is 1, or mx plus b, where m is 1 and b is 0. So you could just have x. All of those are considered distinct linear factors, unless, of course, this was there again, then it's a repeated linear factor. But if 2x minus 5 is only in the factorization once, then that's a distinct linear factor. If x plus 6 is only in it once, same thing. And if x is only in it once, then it's a distinct linear factor. So that's what it looks like. And so what I mean by this is what it looks like once we factor the denominator out like this. Does that make sense, everybody? Okay, so that's what it looks like. We want to know, okay, what does the decomposition look like? Okay, so what does it look like? What does the decomposition look like? This means you put a over 2x minus 5. You put a constant over each of these. The idea is that the degree of the numerator needs to be smaller than the degree of the denominator. So the degree of the denominators here are 1. The degree of the numerator then is 0, which means it's just a constant. And so you'd put a over 2x minus 5, or b over x plus 6, or c or d or something over x, but a constant over the denominator. And then how do you do the integral? How do you evaluate these integrals? So if you have a constant over 2x minus 5, what do? Do you do u sub? Do you do parts? Do you use trig sub? What form are we matching? Is this inverse tangent? Is this log? Is this the power rule? Is this arc sine? What are we doing? So we do u sub, but what form are we matching?
1 over u.
Yeah, 1 over u du. So it's u sub with log forms, which is 1 over u du, or in this case, just 1 over x, and then it's just natural log absolute value of x, but these are all log forms. Does that make sense to everybody? And does everybody get what I mean by these 3 things? So like what it looks like in the problem once you factored it out, what you do as far as the setup for ABC and stuff, and then once you get to the integral, how do you evaluate? This is all very informal, but it's the way to think about how to approach these. Everybody understand? Any questions? Okay. So now let's do the same thing for repeated linear. So what does it look like? Okay, well, repeated linear looks like this. It's like if you have 5x minus 2 to the 4th power, or if I have x plus 7 squared, or if I have x squared, okay, or x to the 3rd, and the numerator is whatever it is. Okay, so these are linear, but they're there more than once. And it's weird that x squared is considered repeated linear and not irreducible quadratic. We'll talk more about that in a minute. But x squared or x cubed, that is repeated linear. It is not considered an irreducible quadratic. Does that make sense? All right, so that's what it looks like. What did we do up here? Well, when it was x plus 5 squared, we put something over x plus 5 and something over x plus 5 squared. Well, the idea is you want all of the smaller denominators that could result in this common denominator. So for the decomposition, which we'll do in purple, if you have 5x minus 2 to the 4th, all the smaller powers get their own fraction. So it could be 5x plus or 5x minus 2 to the 1st. You'd have b over 5x minus 2 squared. You'd have c over 5x minus 2 to the 3rd, and d over 5x minus 2 to the 4th. You know, these would be separated with pluses within a problem, but that's the breakdown. Does that make sense? We'll go ahead and separate it with pluses so it's clear. All right, same over here. Everybody clear? Okay, for x plus 7 squared, we'd have e over x plus 7. And f over x plus 7 squared. And for x squared, we'd have g over x and h over x squared. Any questions on that? I mean, within one reasonable problem, you wouldn't do all this, but this is how you would set it up. Okay, so like we said back here, you know, you have x plus 5 squared. This is one where it just happens there twice, and then you get x plus 5 to the 1st, x plus 5 squared. We know not to do that back up here because these are both to the 1st power, so they're not repeated. Okay, so now once you get to the integrals themselves, there are 2 different forms that occur here. So when it's like a over 5x minus 2, or e over x plus 7, or g over x, those are log forms. And what happens though here? So like something over 5x minus 2 squared, or 5x to the 3rd, 5x minus 2 to the 3rd, you don't do log forms on those. What do you do on those?
It'd be like u to a negative power.
Yeah, u to a negative power. So it is u sub, but it's the power rule. Does that make sense to everybody? So it's no longer a log form for those bigger powers. And like x squared, you make it x to the negative 2. So you have log forms and power rule, depending on which one you're talking about. But just watch that, because when you're doing a huge problem, it's easy to just want to make them all logs, which is what happened with the ones we've done so far, because we were doing the intro. But like this one was log, this one was not log, this was power rule. If this coefficient of x weren't 1, you'd have to do a u sub with the power rule. Not that it's that hard, it's just a lot to keep track of. But we mean, okay, what are we doing here once we get to this evaluation stage? That makes sense? Everybody good? Okay, now, irreducible quadratics. I want to talk for a minute about what an irreducible quadratic is. So we talked briefly about an irreducible quadratics a few minutes ago. So irreducible quadratics are when you can't factor even if you allow for I. So like the sum of two squares is irreducible over the real numbers, meaning you cannot factor that even if you allow for square roots. You could if you allow for I, but we don't. And so you cannot factor that, but you can factor this. So x squared minus 10 factors to x plus the square root of 10, x minus the square root of 10. Obviously, x squared minus 16 factors to x plus 4, x minus 4. So when you have two terms, the sum of two squares is what's irreducible. Does that make sense, everybody? And I should have said this, but what do I mean by quadratic? Just as a quick review. Somebody want to tell us? What's quadratic imply? What's the degree of a quadratic?
2.
Degree 2. Okay, so quadratic is degree 2. So all three of these are quadratics. This one's irreducible, meaning you cannot factor it even if you allow for square roots. When you have three terms, everybody, I think, remembers how to factor like x squared minus 3x minus 4. That factors to x minus 4, x plus 1. And we reviewed a little bit last week about that, and you can review that with me if you want right after class or whatever, but we learned how to factor that at some point. What's weird is in algebra, we probably did not spend a lot of time factoring something like this. So if I have x squared, say, minus 5x minus, say, 4, that seems like it should factor and does not. So like, -4 and -1 are the obvious things to think, but -4 times -1 is not -4. And so if that was a +4, this would factor easily. But since it's a -4, it's not. You can't do it. But if I wanted to like solve that equation, so if I set it equal to 0 and I wanted to solve it, how would I solve the equation x squared minus 5x minus 4 equals 0? How would you do that if it doesn't factor?
You would use the quadratic formula.
Yeah, you'd use the quadratic formula. And so this is not an equation, and so there's nothing really to solve, but the quadratic formula tells you how to factor it. So if I do the quadratic formula and get x equals -b plus or minus the square root of b squared minus 4ac all over 2a, so then I get 5 plus or minus the square root of 25 minus 4 times 1 times -4 all over 2. Then I get 5 plus or minus the square root of 41 plus or minus square root of 41 over 2. The point is not doing that, but that means it factors to x minus 5 plus the square root of 41 over 2 and x minus 5 minus the square root of 41 over 2. And let's not take time to multiply that out and verify that, but if you were to multiply this all out, turns out you would get this. And that's a little weird to think about, but that is the case. And so this does work, and there's kind of a proof of that, but there's a lot of algebra theory there. So this one in calculus, if you have that in the denominator, you would factor it into that. We won't do any examples like that, but you could, and it's not really that much different from this, except that these numbers are annoying. Does that make sense to everybody?
How do you know it's minus, like x minus that?
Yeah, good question. It's because the zeros that like the solution to the equation. If you
Oh,
were
right.
zero,
Yeah.
you're good. But like if you set this equal to 0, the zeros would be 4 and -1, and those correspond to factors of x minus 4 and x plus 1. So -1 corresponds to x plus 1, +4 corresponds to x minus 4. Same deal here. So 5 plus radical 41 over 2 corresponds to x minus that. Does that make sense? All right. And like this one's negative actually. So like really, if you were to simplify it, this would be plus once you dealt with it. But when you look at that, it's hard to know for sure it's negative. Square root of 41 is bigger than 5. So that one is negative, which means if you wrote it as a decimal, you'd have x plus something here. Okay, so this one though doesn't factor. So if I have x squared minus 2x plus 5, how do I know for sure that that doesn't factor even if you allow for square roots? What would determine that? So let's check. So you go x equals -b, so that's 2, plus or minus b squared, so that's 4, minus 4 times 1 times 5, all over 2 times 1. And so you get 2 plus or minus the square root of -16 over 2. That's bad. Now, if we say, okay, that's 4i, then okay, you can handle that. But that's, like we said, complex analysis, not standard calculus. So we don't deal with that in this class. But this means this is irreducible, meaning even if you allow for ridiculous things like the square root of 41, which we do, you do not allow for the square root of -16. And so this is an irreducible quadratic. Does that make sense to everybody? Okay, so irreducible quadratics are when b squared minus 4ac is negative. Okay, so quadratic means it's ax squared plus bx plus c. If b squared minus 4ac is negative, meaning you get a negative under the radical in the quadratic formula, then it's irreducible. That would be true here because b squared minus 4ac would be 0 squared, because b is 0, minus 4 times 1 times 49, which is negative 196, I think, but it's negative for sure. Does that make sense? Over here, b squared is 0, but you get 0 squared minus 4 times 1 times -16, which is positive 64. So you don't have to check that every time. But if it's something where you cannot figure out how to factor it, you need to verify that it's irreducible by doing this. Otherwise, there is a way to factor it. In general, it might mean you can use the square root stuff, but you can factor it whether we can figure out how or not, as long as this is positive. Does that make sense? Any questions? If it's negative, it's irreducible. Okay, so irreducible quadratics can happen when you factor something larger down. So when you factor that one, with both of these, that's not going to happen. But if you have a bigger one, it could be irreducible, or this might be irreducible to begin with. So it's possible this doesn't factor at all, and then we have to figure out how to deal with that. So within partial fractions, what does this look like? Well, it looks like when you have something over x squared plus 25. Or something over 9x squared plus 1, or something over x squared plus 2x plus 1, except that one does reduce, my fault, x squared plus 2x plus 6. So double check, but b squared is 4, 4ac is 24, so b squared minus 4ac is negative, so that is irreducible. If this is reducible, you would break it down into these. But if it's not, then it's an irreducible quadratic, and you deal with it this way. The decomposition for those looks like this. So you have x squared plus 25 in the bottom. The degree of the top has to be smaller than that. Okay, so when the degree is 1 in the bottom, that means the degree of the top has to be 0. When the degree is 2 in the bottom, there's more than one way for the degree of the top to be smaller. What possibilities are there if the condition is that the degree of the top has to be less than the degree of the bottom. It could be degree what? What do you guys think?
1.
It could be degree 1 or degree, yep, could be degree 1 or degree 0. And so the way we represent that is we write ax plus b. That looks like degree 1, but depending on what a and b are, maybe it's actually degree 0. How is it possible that this would really be degree 0? What do you guys think? If a was what value of a would make this really be degree 0? Yeah, if a was 0, somebody say it in the chat. So if a was 0, this is actually degree 0. So by writing that, we're saying, okay, it's probably degree 1, but if not, if it's degree 0, we're just going to work it out and we're going to get that a is 0. Does that make sense? All right, and so same thing for 9x squared plus 1. We get cx plus d over 9x squared plus 1. And we get ex plus f over x squared plus 2x plus 6. All right, any questions on that? We're good? All right. Okay, so then when we do the integrals, let's talk about that in a minute, but let's go ahead and talk about repeated irreducible quadratics over here. That's when you have like x squared plus 16 squared, or x squared plus x plus 1 to the third. So you have an irreducible quadratic, but it's there more than once. So here it's there twice, here it's there 3 times. We're going to deal with it the same way we dealt with repeated linear. Each power underneath it gets its own fraction. And so when we do the decomposition, we're going to get ax plus b over x squared plus 16 to the first. And we're going to get cx plus d over x squared plus 16 squared. And then when it's to the third, each one gets its own fraction. So we get x squared plus x plus 1 to the first, to the second, and to the third. All of them get something x plus something on the top. So first degree or 0 degree on the top. So gx plus h over x squared plus x plus 1 squared, and ix plus j over x squared plus x plus 1 to the third. So we get all those. Does that make sense? Everybody clear? Okay, now to evaluate the integrals. Let's come back and say how we evaluate these integrals in a minute. So if you're trying to keep really neat notes, I'm going to write some stuff in blue down here and blue down here, summarizing how we would handle that. But I want to do an example first, and then we're going to come back and deal with that. So I want to look at this problem next. That's what we're going to do. 20x squared minus x plus 32 over 9x to the third plus 16x. All right, so before we start this, how can we tell that we should use partial fractions other than the fact that I've been talking about partial fractions for almost an hour now? How do we know this is partial fractions?
The degree of the bottom is greater than the degree of the top.
Yeah, degree of the bottom is bigger than degree of the top, and the bottom factors. Does that make sense? All right, and so we're going to factor the bottom. You can't do much to factor the bottom. All you can do is take an x out. And we get x times 9x squared plus 16. 9x squared plus 16 is an irreducible quadratic. If that was minus, we would need to factor it further. Does that make sense? So we would need to make it 9x squared minus 16 if that was a negative there. I'm sorry, if that was 9x squared minus 16, we would need to factor it to 3x plus 4, 3x minus 4. But since it's plus, it's irreducible. Does that make sense? All right, so now we're going to split this into the decomposition. So x is a distinct linear factor. So x is linear because it's the first power, and it's only there one time. And then 9x squared plus 16 is an irreducible quadratic factor. And so we get it to there. Does that make sense? Okay, so now we're going to multiply by the common denominator. So common denominator is x times 9x squared plus 16 over 1. And on the left-hand side, that cancels the entire denominator. On the first fraction on the right, the x cancels, but the 9x squared plus 16 does not. And on the second one, the 9x squared plus 16 cancels, but the x does not. So now we're going to distribute the a and distribute the x. So we get 9a x squared plus 16a plus bx squared plus cx. And we're going to carry down this left-hand side. Now we're going to combine like terms, and remember that x is the variable. So you get all the x squareds together first. So we get 9a plus b x squared. We get all the x's, but that's just cx. And we get all the constants, but that's just 16a. Now the polynomial on the left has to be the same as the polynomial on the right. So over here we have to have 20x squared minus x plus 6 or plus 32. So 9a plus b has to equal 20. C has to equal -1, and 16a has to equal 32. Does everybody follow that? Now this part's a little bit easier on this one because we already have C. A we can immediately get is 2. And then we can plug that into the first equation. And then we get B is 2 because we subtract the 18 over. And now I should have left way more room for this integral. So that part's a little bit easier actually, but the other part is not. The integral's harder. So now we're going to rewrite this as the integral of a over x. So that's 2 over x plus bx plus c. So 2x minus 1 over 9x squared plus 16. All right, questions to there? Is everybody good? Okay, and just before we finish this problem, this is what's important about this table is, okay, the way we knew to do this was based on this first line, right? Like when we factored the denominator, we had x times 9x squared plus 16. So that's what I mean when I'm saying, okay, the stuff in green, what does it look like? Well, x like this, 9x squared plus 16 like these, where they're irreducible quadratics, and they're not there more than once, like these are. Then on the decomposition, this is how we handle it. When it's x, we just put a constant on top. When it's 9x squared plus 16, it's like these, you put like ex plus f. And so that part is how we handled this. Then you do the algebra basically the same, although here it ends up being a little bit easier, but basically the same. We do the algebra to solve for a, b, and c. And now this third part up here, man, wherever it was, there it is. The third part up here is how do we evaluate it now that we get to this integral? And so we know how to do these, and we're going to review how to do these. We've talked about them, but it's been a little while. So the 2 over x is a log form. You just take the 2 out, and it's not even just a log form. It is the log integral. But now who remembers what you do when you have something like this. So if you have 2x minus 1 over 9x squared plus 16, any ideas? We have done them. It's just been a while.
Inverse tangent.
Inverse tangent and something else. Yeah, the hard part's inverse tangent. So good. But okay, this would be inverse tangent if the 1 was there, but the 2x weren't. Does that make sense? So with just the 1, it's inverse tangent, or with any just constant. So it doesn't have to be a 1. It could be like a 7 or whatever, but no x. With the 2x, what is it instead? Like if it was 2x over the bottom, that would be log. And so we actually use log and inverse tangent, but we split it into 2 in order to do that. So we go 2 integral x over 9x squared plus 16 dx minus the integral of 1 over 9x squared plus 16 dx. So this part, this third part, is inverse tangent, but this middle part is log, where u equals the bottom. Does that make sense to everybody? Okay, so before we finish that, let's go back up and fill in. When we're doing distinct irreducible quadratic, these are log forms and inverse tangent forms, which is true for these, and it turns out is true for these, but that's a lot harder. And if we have time, we will talk about that tomorrow. If not, we will do it sometime after the test. But all right, so here we're going to use log on this first one. So I'm going to split this into 2 separate colors. So we're going to do the log one in red. So u is going to be 9x squared plus 16, and du is going to be 18x dx. So on this second one, I need 1 over 18 outside and 18 inside. The first one is easy and is that. The third one we'll do in green. We need, for inverse tangent to work, we need this 16 to be a 1. So we factor out the 16 and we get 1 over 1 plus 9/16 x squared dx. And this is also a u substitution. And I'm going to use the letter v, not because it's parts, but because we already used the letter u on this middle one. So v is 3/4 x, and dv is then 3/4 dx. So, okay, so we get 2 log absolute value of x. And then for the middle, we get 1/9 integral 1 over u du. And then for this part, we get 1 over 16 integral. We need 3/4 inside, so we need 4/3 outside. So we put a 4/3 there. 1 over 1 plus 9/16 x squared times 3/4 dx. And now this one ends up being 1 over 12, because it's 4 over 48, which reduces 1 over 1 plus u squared du. And the log part carries down. And now we'll put the final answer all in blue because that's what we're doing to begin with. And so we got 2 log absolute value of x plus 1/9 log absolute value of u, but u was 9x squared plus 16. And then minus 1/12, I'm sorry, these were v's on this green one. So this should be 1 over 1 plus v squared, and this should be dv. And then this is 1/12 inverse tangent of 3x over 4 plus c. And this in the middle is the answer. Does that make sense? That is a lot in one problem. But do we follow what we're doing? Please ask, because I know this is not easy. So please ask if you do have any questions on that. This is the answer of this problem. Okay. So, we sure? I'm going to choose to believe you. Okay. So, when we go up here, this is a summary of kind of all the stuff that's going to happen with partial fractions. So we need to know how to handle the decomposition. Once we get the decomposition solved for A, B, C, and so on, we need to know how to then handle the integrals. Repeated irreducible quadratic, we're not going to do a bunch of those because they're just very, very involved. These can involve inverse tangent. They can involve log. They can involve inverse tangent. And they can actually involve trig sub. And they don't look like trig sub because they don't have square roots. But you actually did one on the homework where it was in this form. And I think they gave you like something over x squared plus 16 squared. And you had to like let x equal 4 tangent theta, and it worked out. And my bad, there's also power rule. So you have power rule, log, inverse tangent, and trig sub. And all of those can come into play when we're doing those. They can also involve what's called completing the square, which is what's involved in these and involved in these. And that's all technically fair game, at least up through distinct irreducible quadratics. But we're not going to spend any more time today talking about that. Tomorrow, I want to go through some more examples. So give me a minute because I want to kind of summarize. Any questions before I start doing that? Sorry. Everybody clear?
Is all of this going to be on the exam?
So everything through today that we've actually covered is going to be on the exam. You will not have any integrals that you have to evaluate that involve these. Does that make sense? So
Okay.
you may have to know how to like set it up like this. You know what I mean? Like you may have to be able to tell me, okay, if you get this in the bottom, what do you do? But I won't make you actually evaluate one where it's a repeated irreducible quadratic. You may have to evaluate any of these. Does that answer the question?
Yeah, thanks.
Okay, yeah, no problem. And then it's also going to cover what we're going to do tomorrow. But the stuff tomorrow, so what we're going to cover tomorrow is what happens if there's a middle term here. Everybody see what, so like that ends up being log and inverse tangent as well. But we haven't talked about what happens when there's a middle term. It is like the problem we just did, but it's harder because to get this with a middle term to match inverse tangent requires a lot of creative algebra. So we are going to talk about that tomorrow. And then the other thing we're going to talk about tomorrow is if these conditions don't hold. So we're going to have to be able to factor the bottom or this doesn't work at all. But if the degree of the top is not smaller than the degree of the bottom. And so there are ways to deal with that. And it's not that hard. It's just some algebra we probably haven't seen in quite some time. And so those two additional cases will potentially be on the exam. So we have to know how to handle those. And we will talk about that tomorrow. But so what happens if the degree of the top is not smaller? And then what happens when there's a middle term? I want to talk about real quick though, what I want you guys to work on. So because it's test week, we're not going to have any brand new homework this week, but you have the homework from last week that's due tonight. So that you do need to do. So I think, what is it? There's two websites right now that are open. Is that right? Somebody verify. I think it's 2. I emailed you guys last week. Yeah. Okay. So there's the 2 websites that are due tonight. Thanks, you guys. So those are due. And then there are 2 worksheets. And I want to pull them up. I'm not going to do a WebAssign on partial fractions. I'm going to give you these 2 worksheets and you have the answers. But you don't have worked out solutions. So you need to work them out. But like part of the reason you don't have worked out solutions because I didn't want to make them because they're miserable. So sorry about that. But part of it is it's not that helpful to look through this. And I am happy to work through them with you if you want to. But you have the answers and you could check to see whether you're doing them right that way. But I want to show you the handout and I want to talk specifically about which ones to avoid for now. Give me 1 second. So they're in Unit 1, Folder 8. which says, I'm sorry, folder 7, which says partial fractions. Unit 1, folder 7, and there's 4 files, but 2 of them are the worksheets and the 2 of them are the answers. I understand that you have a lot to do this week and you have a lot to do in general, which makes sense. And because you're studying for the exam, you can pace things how you want on this stuff. But here's what I would recommend that you do. So this is the first worksheet on partial fractions. Is that shared right? Yeah. Is it showing up? Yeah, okay. All right. So what I had asked you to do before today's class is make sure you can do the first 3 problems. If you haven't done that yet, you should for sure do the first 3 problems based on what we did last week. Based on what we did today, you should now be able to do 5 through 8. Okay, you should now be able to do 5 through 8. Based on what we've done today, you should not yet be able to do 4. And the reason 4 is a lot different is because problem 4 is an irreducible quadratic, or it has an irreducible quadratic in the denominator, which means we got to figure out how to do that. And that's one of the things we're going to talk about tomorrow. But problem 4 looks a lot like these others and is much, much different because it's irreducible. Number 5 looks like the first 3 and is a little different, but when you factor it, you get x plus 3, x plus 3. So it's a repeated linear. So you know how to do that now, but we did not know how to do that last week, which is why I didn't want you to do number 5 yet. And then now we do know how to do all 5 through 8. So what I would recommend, obviously finish the web assignment that's due tonight. I would recommend that you are completely comfortable with the 8 problems on this sheet before the test. We'll talk about problem 4 tomorrow, but the 8 problems on this sheet, make sure you're completely comfortable. The second sheet is coming up now. It has a lot more practice with partial fractions. And depending on how much practice you feel like you need, you now have 15 more problems. And then these we'll talk about tomorrow. You should do those. But you should do as many of these as you feel like you need to be comfortable for the exam. Does that make sense? So like those 8 problems are kind of the absolute basics that we need to really, really get. And when I say basics, I certainly don't mean easy, but that's like the basis of all of this stuff. And then these are more practice with this. There are a few here where the degree of the top is not smaller than the bottom. Here, the degree of the top is bigger than the bottom. So these are practice on how to deal with that. There's some at the bottom of this where you're writing the form of the partial fractions decomposition. And that's something that's very, very easy that we'll talk about tomorrow. But tomorrow we'll talk about degree of the top not being smaller, and then what happens with an irreducible quadratic with a middle term. And then we'll talk a little bit about this general form of the partial fractions decomposition. That stuff is all fair game for the exam. Wednesday, we will not have a new lecture. We will, so let's go ahead and talk about that. Give me one sec, there we go. Okay, does that make sense of the questions or on the homework, you guys? So I'd make sure you do the first worksheet completely, and then, obviously it'd be ideal if you did the whole second worksheet, but I understand that you have to study for the test and you have other classes too. So whatever is best for you. I'm not collecting any of these worksheets. So you have to do the web assignment that's due tonight, but I'm not collecting anything else this week so that you can pace yourself how you want for the exam. The exam is Thursday. We'll get more information about the format of the exam to you later in the week. At least part of it will be on WebAssign. I think most of you are in my class, but if you're in my class, it's very likely that it will all be on WebAssign. If you're in somebody else's class, that may or may not be the case. But anyway, it'll be similar in format to last time. The time limit won't be as much of an issue as it was on the last exam, but you'll have 24 hours, just like last time. So you can take it whenever you want within the 24 hours. When you start, your time will start. And so, you have to finish it within your period. But you can take it anytime on Thursday. On Wednesday, we'll hold 2 review sessions. So 12:30 to 1:40 will be review session instead of class. So we'll do a review session Wednesday instead of class. And then there will be an evening review session, but I actually have to check my calendar before we figure that out. We'll try to figure out an evening review session tomorrow. So we'll try to figure out what time it's going to be held tomorrow with whoever wants to go to that. So I'll hold 2 review sessions Wednesday, and then no class, no live sessions Thursday. So you'll have 2 review sessions on Wednesday where you can come ask as many questions as you want to get ready for the exam. On Thursday, once the exam is kind of open, then I really can't be available fairly to anyone at that point. So unless it's like a technical issue, Thursday is pretty much you're on your own Thursday, but Wednesday I'll help you as much as possible. And then obviously I'll help you now if you have questions, and then tomorrow we'll do a little bit more material and I can answer questions then. Okay, that's it for today.